Welcome everyone, and thank you for joining us today. Today's webinar is presented by Sports Field Management Association. This week, we continue our four-part series of post-conference education. Our featured speakers today are Dr. Colin Campbell, Dr. Neil Hansen, and Dr. Brian Hopkins. Dr. Colin Campbell is a soil physicist and senior research scientist at Meter Group, where he specializes in sensor and other technologies to manage moisture in the soil and other systems. Dr. Neil Hansen is a professor at Brigham Young University. He is the chair of the Plant and Wildlife Sciences Department. His research and teaching emphasize soil and water science. Dr. Brian Hopkins is a professor at Brigham Young University. He is a certified professional soil scientist. His research and teaching emphasize soil and water science and management in turfgrass. Although not joining the presentation today, Dr. Ruth Carey, also from Brigham Young University, contributed to the research presented today. Today, they will be presenting water management, cutting-edge tools you may be missing. Attendees will be muted during the presentation. If you have any questions, please use the Q&A or the chat feature. Please type in your questions and they will be answered after the presentation. Thank you for joining us today. You guys can get started.
Great. This is Brian Hopkins. Can you hear me okay?
We can, Brian.
All right. We're having a little bit of technical difficulty, but Colin's going to run the slides and I'm going to talk for a minute and then turn time to him and Neil. So we've been asked to talk about this. If you could give me the next slide, please. So when we look at water management, we are doing a lot of work at BYU. We've got a lot of folks that have helped us. We'd like to acknowledge some of these folks without reading their names, but more than just the authors of this, we have very much had a lot of help. So if we could have the next slide. So, why are we interested in water? Well, one of the obvious reasons is we're in what we call a mega drought. And if we could go to the next slide. If you go, for example, to NASA's drought page, you can see, for example, one of the two stories here, one of them is drought in the northern Great Plains, and the next one is a story about Lake Powell being, at historically low levels. We have a serious drought problem, and it's not just been 1 or 2 years; it's been a lot of years. So we're very interested in that, and particularly in the West. All right, let's go to the next slide, please. That affects sports turf. We get water restrictions. We had some water restrictions in California in recent years. We've had water restrictions in other parts of the West, and not just the West either. And sometimes that affects our ability to take care of our sports fields. Let's go to the next slide, please. Again, if you look at the U.S. Drought Monitor, most of the time, we've got some kind of drought happening in the West. Like this particular time frame, it's not bad in Texas. Other times, it's bad in Texas. This particular time frame, it's very bad in Utah, California, et cetera. We are commonly experiencing these problems in the West. If we look at the next slide, we'll see that go ahead and click on it again. I've got animations here. On the y-axis, we're looking at the average annual precip. So the higher it is, the more annual precip. And you'll notice states like Utah, where I'm living, is towards the bottom. And then if we look at the x-axis, these are projected changes in population. So that's going to be pressure that's put on the existing water that we have. And you can see that we've got some states, again, Utah is there, Colorado, we got states that have a lot of projected growth. And so go ahead and click it again. This next group is where we're really low in water, but particularly this on the end. Go ahead and click it again, please. All right, so bottom line is we've got a problem, and it is regional. But it's not just in the West. If we look at the next slide, we'll see that we get problems in other places. This is from several years ago, but look at how bad the drought was at that particular time. It wasn't so bad in the West as it has been recently, but in the Midwest, it was terrible. But even look down in Southeast United States. You pick a place in the country, and we get into water trouble. And so particularly for sports turf, where we're under constant pressure to have performing surfaces, we've got to think about our water. We've got to have functioning irrigation systems, but we've also got a responsibility to conserve. So look at the next slide, please. We get these kinds of things. We get cities, opting to pay people to take out their water in their lawns. And I'm not necessarily against that in some places. In fact, last summer, I took out the parking strips at my house because they just weren't very functional. And I put in a system, a water-wise system, and I'm using 15% of the water that I was using previously. So it makes sense in some cases, but we want to be able to have our grass. If we look at the next slide, we can see that all kinds of benefits. There's lots of things, sports and activities is just one of them, but also helps cool the urban heat footprint, helps produce oxygen, and a lot of reasons why we want to do that. We need to be better at saying that, be better at promoting, hey, it's important to have plants in the landscape. Let's go forward. So, okay, that's kind of the obvious reason to save water, but what other reasons? Let's move forward and we'll look at some reasons to be water wise. I'd like to talk about our true health versus cosmetic health. I run into things all the time where we get kind of a false sense of good health. Let me give you an example of a friend of mine. He was very overweight, more than me, and he was really desperate to lose weight. So we went on this really extreme diet. And according to weight loss, if that was your only metric, he was successful. He lost a ton of weight. But after about a year, his doctor said, "You are not healthy, dude. You're in trouble." And it was because of this extreme diet he was on. Yeah, he was losing weight and he looked pretty good, but his health wasn't good. And I'm telling you that sometimes that's what we see. How do we get truly healthy grass like we've got here at Lavelle Edwards Stadium? This picture here, we got nice deep roots on a sports field that's looking good. Let's go to our next slide, please. So I see these kinds of things when I think about plants, and a lot of times when I'm in a consulting type of a situation, I've got a problem in the environment with the plants that I'm growing. I'll view it in this way. I ask myself, what do plants need to be really healthy? They've got to have each of these things. And so in order to really be healthy, I can't just focus on one of these. Next slide, please. So if I get too much water, and I'm going to throw nitrogen in here too, because one of the things we tend to do is we tend to talk about those two things in silos. We tend to talk about water, and then separately we talk about the nutrients. But we're going to today, part of what we're going to do today is put these two together because they're very inseparably connected. I often see, though, that in a sports field environment in particular, but just grass, people who are taking care of grass, oftentimes we throw on extra water and extra nitrogen. And in the short term, that oftentimes gives us, some reasonable looking grass. Looks pretty healthy, but is it really healthy? That's kind of the question. Or is it more of a kind of like makeup? I'm putting makeup on, and I'm getting kind of a false sense of beauty. All right, let's move on. Excess is bad for the environment, for water conservation, nutrient pollution. Let's look at the next points here. We can just kind of scroll through these, Colin, please. Plant health is one of those things. If for long-term health, we need to keep these things in balance. We need nitrogen to be at an optimal rate. We need water to be at an optimal rate, not an excessive rate. Let's go to the next slide. This is one of my favorite pictures. I love this picture. If you kind of click on this, Colin. All right. So the plants there on the right, the grass that's growing, this is being grown in a hydroponic system in an environmentally controlled growth chamber. We're supplying everything artificially. These plants are growing in that bucket right there of nutrient solution. It's got high nitrogen. You can see they're excessively green with excess shoot growth. And look at the roots. They're much smaller compared to the ones on the left. If you click on that one, You can see this is my optimum rate of nitrogen. Yeah, it's less green slightly, but still looks pretty good. I got nice steady root growth, which means I don't have excess and I'm not mowing as much and I'm not putting as much pressure on that system. But look at those roots. Which are the more healthy plants? Now, a couple other side notes. If you click on the next thing, we'll see that I like to kind of point this out. It's like sometimes we get grass that's 2 inches, its roots are 2 inches deep, but genetically, these grass plants can grow much deeper. And these are being mowed fairly short, but yeah, look at the root growth. That's tremendous. And then if we look at the next thing here, we can see that I also want to point out that we're actually growing these roots submerged in water, which kind of defies maybe what you might think. It's like, wait a minute, we're going to tell you excess water is bad. And yet these roots are growing submerged in water. How can that possibly be? Well, too much water isn't the problem. What happens with too much water is I don't get enough oxygen. And the way I can grow these plants in this hydroponic chamber is because we're bubbling oxygen into that nutrient solution. And so it's got plenty of water and it's got plenty of oxygen and it's got its nutrients too. All right, let's move on. So coming back to this slide, and let's click the next thing here. We're going to kind of walk through some of this. Why do I need to get the water right? I mean, what's important about that? Let's click the next one. So obviously water, it's important to get the water right so that we have proper hydration. If I don't get enough water, that's, frankly, is there anything more important in what we do than in doing that? Because if it's too dry, it doesn't matter what else I'm doing right. It's a problem. All right. Energy. I've got to have energy from the sun. Actually, water, having proper hydration will affect that. If I'm too dry, close up the stomates, I don't get good growth. It's an anchor in the soil. And that's important for us, especially in sports turf, because if it's too wet, I get into trouble. I get not only poor conditions for the plants in terms of their anchors, but I get poor footing for my athletes. All right, now I blended these two together because they're related. When we talk about nutrients, we have non-mineral nutrients, including I have to have oxygen. Now, for the shoots, there's plenty of oxygen. The air we're breathing, 21% oxygen. But if I get compacted, I get too wet, I have an absence or a minimal amount of oxygen in the root zone. Now that also is related to over there on the right, we can accumulate respiration gases, which can be toxic to these plants. Okay, and the next thing shows that we get minerals. And I've some of these things are not as related to water. Some of them are slightly related. You can see those in blue. The ones that are very much related to especially excess water, and nitrogen would be the leader of the pack, are there in red. We know that. We get too much nitrogen, we leach, we have denitrification. But one of the things we're going to show you is that there's some other things. We can actually dilute the system. So not only are we worried about leaching, but we can actually dilute it to the point that the plants they're taking up water, but you've got so much water there that we've diluted the nitrogen. So Colin is going to talk about this in a little bit. All right, and then we also have pest pressure things, weed competition, especially annual bluegrass. I bet every one of us has got annual bluegrass problems. Excess water makes annual bluegrass problems worse. If I have an oxygen deficiency, I'm too wet, those plants that want to grow deep, they're struggling and they're being forced to root shallow, and they're not adapted to do that as well as annual bluegrass. Annual bluegrass does really great with too much water because it's used to and is adapted to having shallow roots. All right, let's move on here. Disease is another one that's kind of obvious. If I'm too wet, I'm increasing my chances of disease. So another reason why we want to manage our water better. All right. Now, can we conserve water and keep the grass healthy? I would argue yes. And most of us need to do a better job, and we surely can do a better job. All right, so I'm going to turn the time over to Colin. Thank you so much.
Yeah, thanks, Brian. So I'm going to talk a little bit about just the current methodologies for irrigation management. And I'm only going to touch on this because I think you're very familiar with these already coming in and sitting down. I'm just going to pop through a few things that we all know. For example, there are those turf grass managers who just have this wealth of experience and are able to to almost use a sixth sense to keep their grass growing beautifully. But one of the challenges is that usually our irrigation problems and our plant health problems that Dr. Hopkins was talking about don't show up visually. And so even though we may have a great field to look at, it's not necessarily being optimally managed. Now, calendar-based irrigation is a great way to go about making sure we get consistent water on the field, make sure that we don't allow the plants to go into stress. But one of the challenges there is there's no accounting for the varying needs depending on how much the grass is using. We like to talk about that in terms of evapotranspiration. And we don't know anything about what's happening in the root zone. I loved how Brian really went into that and stressed that the root zone is at least as critical as what's happening above ground. And we don't know what's going on there. We're not going to be able to account for it. Now, one of the methods popular today is reference evapotranspiration-based irrigation. That means that we're basically depending on weather stations, usually some virtual weather station that depends on those around in the area to control our irrigation. Basically, it's going to tell us, hey, yesterday you lost, a quarter inch of water. You need to put that quarter inch back on. And in some cases, we have irrigation controllers that will actually do that. But one of the challenges is that these are not necessarily local to our turf field. And one of the most important things that I've always been taught that's a really big concern, the ETO or this reference evapotranspiration is only noting how much is going in and how much is going out. It tells you nothing about what's actually available in the soil. And I like that to equate that to you going to a restaurant and the waiter filling up your glass, but he just keeps on filling it. And eventually it rolls over. You're kind of annoyed. You brush all the water off the table and you take a drink and enjoy it. And then the waiter says, oh, you want a little more water. So he comes back and starts filling your glass again, but he fills it with exactly how much you used. And so it starts dripping out on the table again. Now, it's great if you don't really care that there's a big puddle on your table. You can still drink the water in your glass. But you would probably think, well, what is this guy doing? He's just using way too much water. And that's one of the challenges. So I've heard this statement often that since the plant's main source of water, really the only source of water comes out of the soil, the opportunity to ask the plant, hey, do you have enough water, should be focused on the soil and not these other things. Now they're useful. And I think we're going to show you ways that you can use them. But ideally that question gets asked to the soil. There are two ways we can do that. But one way is to use water content. We're going to talk about this a couple more times. So I'm going to beat on this idea. Water content measures how much water is in the soil. And people talk about it like, hey, that soil has 23% water content. Great. There's another way we can do this, which is water potential or soil water tension. Maybe you heard our presentation last year and heard us talking about that. Now, those are the same thing and basically measure the energy level of water in the soil. And it tells us how easily plants can get water from the soil. Now, I'd like to talk about some of these methods for irrigation relating to soil sensors. There are sensors out there that you can just wander around and stick them in your turf. They just have needles on them. They're multi-pronged. You stick them in and a little readout device will tell you how much water is there. Challenge with these are that they're labor intensive. They only provide a snapshot in time of really the upper few inches of your soil, but most importantly, water content fails to indicate if there's optimal water. If you tell me, who's a soil scientist and who've done this for more than 20 years, hey, I've got 23% water content in the soil, I couldn't tell you if your plants are going to be happy. And I don't think you can either, unless you know exactly something about the soil. So one step up from this is actually to put sensors in the soil. They can be installed semi-permanently or permanently in the sports field, and then you can watch the water over time. It makes it easy to spot trends, see if we're under irrigating, based on those trends going up and down and our evapotranspiration number. And we can tell, oh, how much water needs to be added back by these numbers. But again, we're left with a similar issue, that water content doesn't tell us if there's optimal water available. So the question really comes, what does? So what defines when turf has enough water? Well, like your house, that it's not heat content that tells you that if it's comfortable in your house, it's temperature, which is the energy state of heat in a room. Soil water potential tells you the energy state of water in the soil and whether the plant will be comfortable. It's essentially the water thermometer of the plant root zone. We can know if a plant has access to water in any type of soil using water potential. Now, this is the game changer. This is something that we've been working on as a group at Brigham Young University and Meter Group, adding root zone water potential and changing the game of irrigation for field turf. Now, you wonder, well, I've never really heard that there's a comfort zone for plants. Well, one of the reasons is that these measurements haven't been always entirely accessible, but it's not because that this wasn't known. I'm showing you a table from 1972, but the study on turf grass was done in 1964 by a researcher named Morgan. They came up with a number, -24 to -36 kilopascals is the optimal range for turf. And you may be wondering, well, what the heck is a kilopascal? And does it matter? What is a Fahrenheit? I don't know, but I sure like my house at 70 degrees, whatever a Fahrenheit is. And so there is a number that you can use and be able to manage that irrigation water effectively. Now we're going to go talk all about this and show you some fun real world data. But first, I just want to say we can also visualize these nutrients in the root zone. And this is something really important that Dr. Hopkins mentioned. Those things go hand in hand, and we're going to talk about the impact of these two things. We can measure nutrients in the soil with a surrogate we call electrical conductivity. Most people shorten that and just say, hey, it's the EC. But specifically to a scientist, it's pore water EC. But usually they just say EC. And an optimal range for EC is somewhere between 2 and 5 millisiemens per centimeter. I said 1 and 5 here. I'd say it's a little higher. But if you have that right electrical conductivity, things are going to be happy for your roots. Now, just as a note, the tap water you drink is often around 0.2 to 0.5. So if you're measuring in the soil and getting a pore water electrical conductivity around 0.2 to 0.5, you know your nutrients are pretty low. Now, one other thing that's really cool that comes along with a lot of these sensors we're working with, basically for free, is temperature. Measuring temperature in the soil helps us understand what the root zone is experiencing, and whether it's for tarping, where we can increase the temperature, keep our grass a little more lively, or to stave off dormancy or something in the fall. That's something we can get to, and we'll show a couple of graphs here about that as well. Now I'm going to turn the time over to Neil to introduce some of the stuff we did in our project.
Yeah, thank you. Great presentation so far. I've enjoyed this. I want to show you some stuff that we've been working on in conjunction with BYU grounds and sports turf managers. This is LaBelle Edwards Stadium. It's the main football stadium here on our campus at Brigham Young University. And we wanted to try and understand and implement some of these cutting edge technologies in a way that we can, maintain or help improve the turf while also considering water conservation. We started off, this group of students here helped us put out a grid. This was kind of labor intensive, maybe a bit on the science side rather than the practical side, but they measured out a grid of points and then went and used one of the push-in type soil volumetric water content sensors. So they measured that in all these gridded points. And then we've created a map here that shows you that water in the soil is pretty variable. Even in a pretty well-managed scenario. Now this, just for reference, was in the spring before sprinklers had even been turned on. So this is kind of a variation, not due to sprinkler patterns, but just to the way that field lies. And I'm sorry, the colors are a little bit confusing. In this case, the blue is actually a little drier and the red is wet. So you have these kind of two drier areas on the north and south ends of the field. And also you can kind of see a little drier along the crown. The football field is got a crown in the center and tapers to the sides. And so we definitely see a little bit wetter conditions along the edges. So this is insightful. If you're trying to understand how to manage water in this field, we need to understand that it varies. And another way, if you'll advance that, Colin, to look at that we also flew a drone over the field. On the far right-hand side, the image that you see is kind of the processed image, the bare color image of that field. But when we process that with a vegetation index, taking specific wavelengths of light and color bands, again, you can see variable patterns in the health of the grass itself. So on the previous slide, we were looking at what you see in the ground with those push-in water sensors. This is what you see at the reflectance of light on the surface. Again, a lot of variation there. And Colin, before you advance, could you go back to the previous slide for 1 second? We really wanted to get better information about what's happening on this field in time as well. We decided we were going to use some of these sensor techniques that Colin introduced to you. And we'll use this map to kind of help us figure out where to place the sensors. And so up in that kind of north part of the field, in that blue zone, and as it's sort of transitioning, we put a set of sensors there, and then down, yeah, Colin, if you can kind of hover, yep, right where you see the mouse there, we put a second set of sensors there to kind of represent some of the variation in the field. So go ahead and advance 2 slides. This is just kind of the unboxing of the sensors that we purchased. We got these in cooperation with Meter. And in the center there, you see the cables. We deliberately got these with kind of longer than typical cables because we need to get the sensors out in the field, but the data loggers that they hook up to outside of the playing area. And I'll show you how we did that in a minute. At the top, the 2 sensors that are kind of the cylinder-shaped sensors are the essentially weather stations. They collect the weather variables. We installed those. And then the 2 types of soil sensors that Colin talked about, the water content sensor, the one with the needles. Those are fairly easy. I'll show you how we installed those. And then the water potential sensor, the little ceramic disc. Okay, so go to the next slide. It was a fun day, and we had a lot of people come out and watch and take pictures of this. But obviously, with a high-profile field like the stadium, anytime you're putting something in the ground, you've got to make sure you're taking care of the turf and making sure it's ready for its use and its playability. So what you see here is we used a ditch witch to cable those sensors into the ground. The top right inset picture there, you can see we pushed the cables from the sensors through the knife that pulls those cables through. And then on the bottom right inset picture, we dug a hole at the point where we want the sensors to stay, and then pulled those cables back through the grass. So yeah, in this view, now you can see the ditch witch is pulling the cables through. It does leave a little bit of a scar, but we were really pleased actually with how well those installed. Next slide. At the edge of the field, I'll show you here in a second. In fact, why don't you bring up one more slide? Yeah, here in the top right photo, one of the biggest challenges of this field is there is a solid concrete wall about 12 inches thick that separates the grass from the artificial turf around the perimeter. So when we trenched over to that, we had to dig another hole and bore the cables through that concrete wall. And then we came up the side of that concrete wall and passed the cables underneath the artificial turf and then into that box. That was an existing box that we were able to put the data logger inside. So it took us a few hours to get those installed. And then the next slide will show you trying to get the turf grass back in place. There on the top, you can see the actual sensors, the 2 types, the one with the needles, those white rectangles, and then the ceramic discs. Those are inserted into a slot and kind of packed back in so that they have good contact with the soil. Then we backfilled the holes carefully and replaced the turf on the surface. Then in the next slide, you'll see that we used a roller to press back down what was lifted up by the ditch witch knife. And at the end of that, a few hours of installation, that's kind of what you saw, a little bit of a scar from the hole and the trench, but pretty minimal. And within a few weeks, those scars were pretty much erased and looking good. Cut this last set of pictures here. We also did this on a soccer field. And in that field, we did not have the stadium enclosure box to put the data logger in. So what you see in the middle there is we put the data logger on the underside of a sprinkler valve box. And that seemed to work out pretty well too. So that, again, that we could have the sensors, you could see the scar of the trench, bringing the cable over to the data logger. So yeah, I just kind of wanted to show you that story of how we got those sensors installed. And now we'll show you a little bit about what we've learned from looking at the data.
Thanks, Neil. And it's back to me just to talk about some of this stuff. And the first thing I mentioned earlier was that I said, hey, we're going to talk about the evapotranspiration and those data later on. And one of the most incredible things about our research last summer was that we had one of the most long cloud-free periods that I've ever experienced. And you can really see it here in the data. This is reference evapotranspiration. This is a value every single day of how much, or an estimate of how much the grass used. So we're sitting at about a 1/4 inch after our installation through the month of June, and you can see it trends off. This actually is a moment when we took the weather station down for the football game that was at Lavelle Edwards Field. Thank you, Neil, for grabbing that. So you can see that if you just carried on with your normal irrigation patterns, Brian mentioned, hey, I was just irrigating at my house using kind of standard practices. If you just kept hitting that through the rest of the summer, about a 1/4 inch or 3/10 of an inch, you'll be way over irrigating even into the month of August, when it just gut feel is a really dry and a month where you have to apply a lot of water, and you'd probably be missing it. I mentioned there was an optimal level for turf grass irrigation that Morgan in 1964 put out. Now, we've done a little study a little later than that in 2015, and we decided that an optimal range was about -10 to -100 kilopascal in the ASTM spec turf grass soil that we were growing in. So here's a little experiment we did. This is from 2015. This is on the BYU campus. And initially, we were irrigating with a calendar-based system. We didn't know much about, or we didn't take into account what was going in the soil, going on in the soil. And here at 10 inches in the soil, we irrigate here. This is water content. It's about 15 to 20%. We irrigate at the top level, and we see a little bump in water down at 10 inches. That's water we're not getting back. That's going down to the aquifer, and it's also taking our nutrients with us with it. Also, here is our water potential line. That's over on this graph. And basically, we're at a maximum level. Nothing's happening here. And we look further down, nothing's really changed. We are irrigating on a two-day cycle. Here's a syringing where we're trying to just cool that grass in the middle of the day. Another irrigation event, nothing's happening here. Essentially, we're overwatering. And we decided, hey, we need to run an experiment where we figure out how to water optimally. And I'm not going to go through that. We learned a lot of good things. There's another seminar that we've done on this. Today, I'm just going to focus on what we did to try to optimize it. After some work, we found that we could irrigate at a certain level and not jump the 10-inch level water content. And for our water potential, we were still at a really nice level. That's basically as wet as we need to be. It was above -10 kilopascals. What we did then was actually let it dry down for a couple of days down to this level. So we can even see in this water content data, one of the fun things you can see there is just the stair stepping. So this is the daytime water use. And of course, there was a certain amount required. We wouldn't expect that to be exactly the same every day because evapotranspiration requirements change daily. But there was a point where even though we required some water through evapotranspiration, our grass simply didn't use any. And that we considered a point where it was starting to go into dormancy. It did at the 6-inch level, but not at the 2.5-inch level. And this one, we decided, okay, that's about, you don't want to go any further than that. That was about -500 kPa. So a real low level of stress or a level of stress you wouldn't want to go to, essentially. So with this work, we figured we were ready to go and start working on other projects. And one of the projects we worked on is an ASTM green at the Palouse Ridge Golf Course. This is a premier golf course on the Washington State University campus, where we partnered this last year to try to help them reduce water use. Similar to Provo, Utah, Pullman, Washington was under drought conditions, and they'd already burned through their kind of reserve allotment of water, and they were paying a lot of money. And they said, hey, can you come in and just help us get a handle on this? We did it in several locations. This is the practice green here. And I just want to show you what we did once we installed this kind of around the 1st of July. We started reducing our water application here, and this is water content. This is over in this axis. 15% should look familiar because we just talked about that. And we just slowly backed off. We were irrigating still, but backed off to try to see if we can bring this water potential down. Here's the top of the optimal range, down into the optimal range. We got a little bit beyond what we wanted to do and started bringing it back up. We said, okay, that's a little too much. Let's increase it a little bit. You can see that it's a little bit difficult to do this, to get used to it while we can do it. And it takes a little tweaking. But after a little while, we kind of figured out what range we were needing to be in and starting to dial that in. And I'd like to show that just to give you a contextual feeling for some of the other things that we saw in this effort. Again, this is back to that ETO, the reference evapotranspiration graph I showed earlier. The thing I want to bring out here is we're back on the BYU campus now at Lavelle Edwards Field. And even though you may not have a gut feel for it like I didn't, we actually lose the need for water over this season when we go from June into July into August. And by late July, we're at a 3/16 of an inch maximum that the grass needs. Into September, we're down to an 1/8 of an inch, and then into October, we're on a 1/16 of an inch requirement. If you're not dialed in and knowing that you're got to pull your water back, you're over irrigating quite a bit. So here's Haas practice field. This practice field was on native soil. I showed you all the data so far have been from a grass field. In native soil, the capacity to hold water is a little bit higher. And so we set our goal a little bit lower for our water potential, where we say our goal probably is around -20 to -100 kilopascals in this native silt loam soil. You see, this is a beautiful practice facility. Grass is gorgeous. Mike Haas manages this and does a great job. And so we were just trying to pop in there and say, hey, let's see what your water's looking like. Let's see if there's opportunities to tweak it to improve things. So here's the Haas practice field during the summer. I put together a couple graphs. This is what we're going to look at over and over for the fields that we talked about. This is water content now in this graph, and I separated the water potential into a different graph. But I did put a little green range for our optimal area for water potential. And so this is the daily water content change. And it's nice to have that because our water potential was so high that it didn't change during the summertime period. But we see a regular irrigation, which I can say is pretty amazing that we were as consistent. And Mike has this dialed in through the summer to be very, very consistent. But we're also seeing some increase in water every day at the 10-inch level or 12-inch level, which means that's water that's getting down below the root zone that the roots aren't able to access. It's moving any nutrients that are in the water down below the zone. And we have a problem here where we've got the water above the optimal area. So essentially, this is a reminder, we're sitting here and that water's kind of going over the top of the cup. Here's later in the fall, in September into October, we're reducing the need for that water. As I showed you in the ET data, we see a less frequent irrigation. We're still being really consistent between 30 and 35%. But we're generally trending up, and we're still seeing increases in water at that 12-inch level and no change in the water potential. So they're still above the optimal zone. Now, if we go over and look at this other measurement we can get with these sensors, the pore water electrical conductivity, you might remember I started this off saying, hey, our optimal zone is between 2 and 5 millisiemens per centimeter. And really this field is doing great in terms of its pore water electrical conductivity. And you might suppose that that's going to be the case because we're dealing with a native silt loam soil, which has a lot of cation exchange capacity that's going to be buffering those nutrients. So no problem here. We're just seeing a little bit of water on the high side in terms of what would be optimal for that field. Let's jump over to Lavelle Edwards Field, where we have 12 inches of ASTM spec soil. It was originally designed for 9 inches with a perched water table. But because of top dressing over the years, we've increased the level of that field up to 12 inches. One of the problems is we're no longer wicking water up from that perch that we're trying to set up. And we're actually creating this dry zone, quote unquote, still very wet, but a dry zone in between the upper and lower measurements we made. And I'll show you what that looks like here. We want to be super careful with this turf. It's a premier turf. We get to watch it on TV, and that means we got to make sure we have the optimal irrigation done. So -10 to -50 is our extremely conservative estimate for water potential. And so here's a few graphs now that I'm going to show you for water content for north and south. And then I'm going to combine the water potential of both the north and the south in one graph. So right now look for the stars. This says where we're at. Again, we're talking about water content from July or from the 2nd of July, 1st of July up to July 18th. So this is a really hot period during the summer. And remember our optimal root zone water content that I talked about from our study in 2015, it dictated about 5 to 10% would be optimal. If we look up here, everything's above that optimal level. Our water contents are pretty high. Now our 2-inch zone, very wet. It is slowly drying during this period. The 6-inch zone is still very wet, but it's drier than these other two. That's because of that perch water table that's supposed to be set up, but because it's so deep, we're getting this kind of stretching of that capillary water, and it's not getting up to the surface. So this 6-inch level is drier than the others. Still lots of available water down here, and we're washing a lot of water down to 12 inches. Now let's look at the other on the south side. We're thinking about, hey, how consistent are these data? And they are pretty consistent. Now the 2-inch data is a little bit higher than the 12-inch data, but they're still both high. We have the 6-inch, which is still very wet, as I said, but the drier of the three, and we're still above this optimal root zone water content that we just saw in the other experiment. So it's not going to be surprising to you when we look at, now this is our south data, we looked at the north and the south, when we turn to water potential and say, hey, what's happening in the north and the south? Now I've kind of color coded our optimum level of water. This is where no matter what soil type we're in, if we're in this region, we have the optimal availability for water. And it shouldn't be surprising based on that other experiment we did that we're all the 2-inch sensors north and south and the 6-inch sensor here on the north. We actually unplugged the sensor, so I can't show you the other 6-inch sensor. I just took it out. It eventually was reading the same thing. They were all wet. And so we're just irrigating above the level we need. In the fall, we see a very similar story here. We run from mid-October or mid-September into late October. These are the beginnings of the fall rains. These are actually a rainy period. This is a hand watering event, we believe, because maybe we got a little dry spot. I'll show you what that looks like in terms of water potential. But again, the 6-inch sensor is drier than the other two, all running pretty wet. That's the north location. If we go to the south location again in the fall, similar story, all pretty wet. The 2-inch is very wet up here at 25%. The 6-inch is more to the zone we would expect. It's still a little above our optimal range. And so the one thing that we did notice, and this is where that hand watering came in, we finally dropped a little bit in our water potential. It approached the top of our optimal zone at one location, the 2-inch at the north site. But in general, we're still well above our optimal zone in terms of water potential. Now, what are some of the consequences as they tie in here? This is a really important thing to think about, and something that we could measure in the field. Now, we already went through the Haas field electrical conductivity. Now, again, this is the optimal zone for electrical conductivity, and the Haas field is doing all right. It's nice buffered soil with a good silt loam with high CEC. But we can't say the same for Lavelle Edwards field or stadium, because Lavelle Edwards, we're working with this ASTM spec soil that's mostly geared to try to drain water. And drain water, it does really well. There was a huge rainstorm several years ago there, and it drained all that water just in a matter of an hour. Just amazing ability to drain. But that also means that water moves through it when we irrigate in a similar way. And it's pretty clear that our poor water electrical conductivity is on the low side here, and is across this period, same period I've been showing you from the 1st of July up to 18th of July. It's interesting to see where tap water is, and I noted this in red. So if we're drifting down toward tap water, that means we're irrigating with that just municipal water, and most of the nutrients that the grass are seeing is just what's in the water, which isn't going to be effective, and creates challenges for the competition of weeds, for example, versus the perennial bluegrass that we're trying to have be successful there. This is our poor water electrical conductivity in the fall. And once again, we see a very similar trend. It's lower than it was. We had an interesting spike here. There was, I think, some irrigation done. Maybe it's a little nutrients applied a little here. But the thing that I really want you to focus on is when we actually started to get these rains coming in and washing down through the soil, that we're dropping down below tap water. That's because rainwater, of course, is pure. And so when we get a lot of that water coming through, we have even less nutrients available to the soil. And again, we see the same thing in the Haas field, where that drips with the nice heavy rainstorm, but still we have enough buffering that we're not wandering outside of kind of what we think would be proper for the root zone. And this is a concern because, of course, when we're going in the fall, late fall, we're wanting this grass to slip into dormancy and have adequate nutrients for that process. So another thing we just got as a part of this study, which is soil temperature. And there was at one point they went and tarped Lavelle Edwards Stadium, and I highlighted this in blue. And this is Haas Field here in green. This kind of purple reddish, these traces here, this is the Lavelle Edwards Field. And you can see the impact very quickly of tarped versus untarped, that we have a 4-degree Celsius difference. So an 8-degree Fahrenheit difference between those two locations. So tarping made a huge difference, even in the middle of October, where, this is, so we're 10 to 20 Celsius. That's 50 to 70 degrees Fahrenheit. So it's still relatively warm, but you can see that there's some pretty substantial management impacts on the grass from doing some of these things. So what did we learn from this first season? Well, not surprisingly, the fields were watered well above optimal. And the point of this stuff was not to poke it at those people who are working out doing this. Mike and John are great people. They work super hard to make those fields look great. What we're trying to do is just put together additional tools, additional insight, so that they can use and conserve water like they really want to do, and still grow a beautiful grass surface. It's also challenging to reduce water due to previous experience, like hotspots. Their hotspots were popping up, and we're talking about how much water was available, and that became challenging. When we tried to put together grass to help them out, I love grass, but I'm a scientist. We realized we need to do a little bit better as we're sharing this information on a daily or hourly basis with things that are much more usable for someone who's really, really busy. And then irrigation uniformity popped up as a complicating factor for control. And you guys all know about this, but it's something to think about, that as we put in individual sites out there and use some of these tools, we have to have consistent, at least understand our variability and maybe work with others to improve that. There's also a challenge of finger flow in the soil, where water will go down one spot and maybe not another because of hydrophobicity. And finally, just some other things we learned. Water potential does provide real-time water availability, which was huge. We suddenly got this picture, a game-changing picture of what was going on in the soil. And there were opportunities to improve. This is not a poke at anybody. It's just saying, hey, we got a window into something we didn't before. There might be steps we can do. This hot spot, dry spot question is something that maybe we can take steps on to understand. And I'm going to turn it back over to Neil to talk about, after this year and learning what we did, what's next?
Yeah, and I'll just be really quick. I see there's a couple questions coming in, and encourage you all now at the end here to ask questions. You can voice those or put them in the chat or the question and answer box there. But I think that we have really learned a lot working this first year here at BYU, and there's a lot of need for us to interact with the sports turf managers there to take full advantage of these technologies and techniques. You mentioned hotspots, Colin. John mentions there at LaVell Edwards Stadium, when he feels like he's holding back on irrigation, he sees areas of the field that are looking to him dry. Given the results of the sensors, I wonder if the soil is really dry, or if those may be better described as heat affected rather than dry. So we're gonna help John understand that by doing some point sampling when those hot spots appear, and try to understand those better and how that can help us manage. We want to do a better job, as you mentioned, converting our sensor data to quick and simple irrigation recommendations that John can use, make those easier. And then we have some interest in also translating what we're learning from these sensors onto the actual playability of the soil, of the surface, for both soccer and football, and how that relates to safety for the players and performance. And then lastly, we are going to continue doing some work on remote sensing and how those could be coupled with the sensors to really just to kind of amplify our understanding of how these systems are working. So a lot of exciting things on the horizon as we keep going forward with this work.
Yeah, and thank you, Neil. It looked like there was a hand raised out there, and I'm not a Zoom genius, so maybe you're going to have to. Did you see that?
Yes, I see. Jason has his hand raised, and I think you're good to ask questions, Jason, if you want to verbalize those. And Kristen, can you help us out if our attendees able to ask questions?
They're muted during the presentation, so if Jason, if you could type in your question into the chat, and then we will read the question and answer it.
So while we're waiting, Neil and Brian, what these hotspots, what are your? I mean, this is something we've talked about. If it's not water, if hotspots aren't water, what's your theory?
So the question is if we don't water them?
What is, if there's adequate water in the root zone and we're getting a hotspot, what is causing the hotspot?
Yeah, that's a really tough one. And we need to remember we got Kentucky bluegrass here, which is a little bit sensitive to that. I've run into this before. In fact, I used to team teach an urban soil and water class with Dr. Von Jolly, and he kind of taught the nutrient side and I taught the water side of that class. And at some point he said, you know what, I feel like a hypocrite. I need to go start implementing these watering practices in my yard. And he failed, and his wife was mad at him because he got these hot spots. He got his grass going dormant and stuff. But we went out there with a theta probe, which tells me how much water's there, and he had moisture. And it was just the fact that his grass had kind of been conditioned over time to be a little bit on the wet side. And because of that, he was having trouble with these things going into dormancy because of heat stress and not so much from water stress. So I think part of it is training our grass. I think one of the most important things you can do there, I could talk about that for an hour, and I can't, I don't have time, But just one of the best things you can do is in the springtime, get it trained. Get it trained to do that. So like for me, at my house, I turn on my water early, and I make sure everything's working right, and then I shut it off, and I just don't turn it on, and I don't turn it on until it starts going brown on me. Not dormant brown, but in fact, brown's not the right word. Gray is the right word. As it starts being moisture stressed, then I'm training that grass. I am sending some physiological signals for that thing to be more adapted to going under moisture stress less, or heat stress less. And so it's helped a lot. It's, if you're going to continue using Kentucky bluegrass, it's just going to be a continual problem. I really think there's some opportunities here for research as well with, NTAP or whoever to look at, okay, well, what varieties are less likely to do that? I don't have an answer for that today. But I do think, what we've done today, I guess, let me just in some ways summarize, is it's like, this is really cool technology. This is, as Colin made the reference to the thermostat, right? 100 years ago, we didn't have thermostats, but somewhere along the line, somebody invented a thermostat, and they probably went through some growing pains. And that's what I would describe where we're at right now. We've got some really cool new technology, this being able to measure water potential, but we're having growing pains. We're trying to figure that out. The other thing I would just mention briefly is that, at some point, like using valve in head technology, I think is an answer. I think being able to spot water without having to drag a hose out there, I think that's where we need to go eventually. Now I realize that's expensive and that may not be a short-term answer, but that's really one of the biggest problems we've got is like, how do I deal with these hot spots, whether they be moisture or whether they be heat? I know that was a super long answer. I'm sorry.
That was perfect. Thank you. And we've got a couple more things that I've been kind of writing answers to, but we can answer here. Jason was asking what sensor we were using out there, and I typed it into the Q&A, but we were using a Terrace 21 water potential sensor, Terrace 12 water content sensor, an EC, and an Atmos 41 weather station. These were from Meter Group. So you can look those up online if you want to look for those. And we used a data logger called a ZL6, also from Meter Group. Ray McCauley asked, did we measure hardness or shear strength during the study? I was mentioning that really by the end of this, we had a lot of questions, and that certainly was one of those things we'd like to work on this year. So no for last year, but I think it would be a great thing to measure this year.
Then another question, and Brian, you may want to comment on this. This is Ray asking if we got any feedback from players or coaches on the turf condition that we're working on. And Brian, while you think about that, I didn't personally get information back from players or coaches, but the grounds people that are going in immediately after the game to patch the grass on the playing surfaces. I felt like we were getting, they told me they felt like they were getting fewer divots and repair problems when the soil moisture was getting into that more ideal range.
Yeah, I sort of view this year as kind of a learning year. I don't know, we didn't do a lot different. We were just trying to kind of measure and sort of row and figure out how to use this technology. I think there's a lot more that we can do with it. So I don't know that there was a whole lot to observe as different. The other thing is, frankly, like Lavelle Edwards Stadium, it's already an outstanding field. It's frankly one of the best, in my opinion, in the country. I'm a weirdo. When I watch football games or whatever, I'm watching the turf. I have to watch the game twice. So I watched the first time, I watched the grass. The second time I watched the players. But it doesn't divot up hardly at all, especially early in the season. So it's already in a pretty good condition. So, what we're trying to figure out is like, how can we keep that, continue to have such an excellent quality turf, but frankly have better, because we're struggling with it a little bit. I mean, we've got these hot spots, and it's a little bit of a battle that John has to deal with. But how can we do that, especially as the turf ages? I mean, that's, a lot of, if you're a professional football team and you're replacing your field every year, you're not like the rest of us that, we've got to, this field is more than a decade old. We've got to find a long-term solution to keep these things healthy as long as possible. And, that's the question. It's like, okay, how can we get this better health and give me longer, sustainable grass and do it with less water is the question. But anyway, I think that players and coaches are pretty happy with both of these fields. And obviously we can't let it go too dry. That's going to be a failure. But how can we just maybe slide back just a little bit on that grass is the question.
Colin, here's a question for you. It's in the chat instead of the Q&A, but this is from Ben. Will the water type, whether it's municipal water, well water, or reclaimed water, affect the sensors? And similar to that, will salt or calcium affect the sensor readings?
Yeah, so some sensors out there, some lower quality sensors will have an effect, will be affected by things like different water types. But the sensors we're using, they're actually used a lot in hydroponics. So they'll see electrical conductivities of 12 to 15 and that's hopefully we're not going to see that in these soils, in these systems, and they're not affected by that. So we've done a lot of testing. There's a lot of tests available with higher electrical conductivity that show no real change in performance of the sensors. So it's not something we were worried about on these projects. And I think we've reached, guys, our hour. We're a little over. We don't want to keep everybody too long, but this has been a lot of fun. Neil, Brian, thank you. Kristen, thanks for having us.
Yeah, thanks everybody.
Thank you.
And yes, thanks for joining us. Do you guys have a slide with your contact information? No, that's okay. If not, if anybody on the webinar has additional questions, you can email me and I'll send out contact information for any of our speakers. So
great.
Mine is super easy. Just hopkins@byu.edu. So hopkins@byu.edu, and I can forward you to Colin or Neil.
okay. All right. Well, thanks everybody. Thanks for joining us today. Don't miss the final week of presentations next Tuesday. Check the SFMA website and your email so that you can get registered. So thank you and have a great rest of the week.
See you later.